Okay, so if the fundamental theorem of calculus is this magical thing, we really should ask ourselves, why does it work? Why is it true? Why can we just, if we want to find the area under a curve, just find an antiderivative, plug in the endpoints, and subtract, right? So I kind of want to give two arguments, two slightly different arguments, although they're pretty much the same argument, it turns out, underneath. But let me just take you through two different arguments quickly. So for the first one, let me restate the fundamental theorem. It says that the integral from a to b, so normally we said f of x, but I'm just going to go ahead and put in g prime of x because we said like we're going to anti-differentiate little f and get big G, and we could rewrite it as the following. If we just didn't want to have to state two different functions, we're really just talking about the function g, and we're saying if we integrate its derivative, we just get the values of the function at the endpoints and subtract it. And I claim that there's actually a pretty reasonable way to see this especially if you kind of go back to Riemann sums. So let me, remember, we're going to think of this as the limit. Oops, I don't want to use n, I want to use I. I equals 1 to n of g of xi delta x, g prime, I should say g prime, of xi delta x for, the limit as n goes to infinity, delta x goes to 0. Okay, and so I really want to focus on this expression because remember what g prime is. G prime is the derivative. G prime at x sub I is, well, it's that, remember we say dy dx, or actually I'm going to use dg. Sorry, I meant to say dg dx. So the rate of change of g at the rate of change of g with respect to x at xi, at x equals xi. And that really, though, is really something like, think about a rate of change. A rate of change is the change in g. It's a slope, right? It's the change in g divided by the change in x near x equals xi, right? So when I have something like, notice I can replace this. It's not exact anymore. It's more an approximation, but like this is sort of, I mean, this integral is already approximately equal to this for large n, right? This guy is sort of approximately that for large n. Jeez. And this is approximately, so we can really say this whole thing's approximately, I'm going to replace g prime with delta g over delta x times delta x. But now it really, it's a fraction, right? And look, the delta x's cancel. And so this is really something like the change in g. And I could say even something stronger. Maybe I should say something stronger than near x equals xi. That means from like a little tiny interval, but our intervals are like from xi to xi plus 1. Maybe I should actually write the word 2. It's basically on that little, just like that little tiny change in x, right? Delta x is xi plus 1 minus xi. It's the difference between two consecutive, like it's x2 minus x1 or x3 minus x2. And so when I say this delta x, I mean, this what we get here is this thing is now the sum from I equals 1 to n of the changes in g. But each change is like, I mean, I almost should say like this really probably should have like a subscript because it's really like the ith change in g, the change from xi to xi plus 1. So I think that's probably making it sound too complicated. But what I mean is you're basically adding up, i.e. where this is like this right here is like the change in g from xi to xi plus 1. And so you're basically adding up all the little changes in G. Add up all the small changes in G. Can zoom in a little bit. And notice the left endpoint, now there's a little bit of an issue here with starting at I equals 1 instead of I equals 0, but we're getting almost the whole interval. And as n gets larger and larger, delta x gets smaller and smaller, the points get closer to closer together. So when I say all the small changes in G, I mean really basically from x equals A to x equals B. I'm being a little loose in that it's really from x1 to xn, which is, and x1 is a tiny bit to the right of A. But, that's basically kind of the idea. And so this really is approximately, and I guess actually that's actually the difference is that it's not exactly, but it's, this expression is approximately, let me go back to my white. This whole thing is approximately G of B minus G of A, because if you add up all the tiny changes, you basically get the total change, right? This right here is the total change. From x equals A to x equals B. And so somehow the fundamental theorem of calculus is basically really just saying you're adding up a bunch of small changes to get a total change. So the sum of the small changes, I mean, in some ways, this is a summary. The sum of, let me actually zoom back out. So the sum of all the small changes, it's sort of like we stop at each of those x sub i's, right? We're stopping each of those signposts along the x-axis from A to B, all those little tick marks we've been drawing between A and B where they're spaced out by delta x each time. We're stopping at all those signposts and saying, well, what's the change from here to here? And then what's the change from here to here, right? So actually I might draw a schematic of that in a second, but the sum of all the small changes equals the total change. It's really kind of what the fundamental theorem of calculus says. It's really not, in some ways, when you break it down like that, it's actually not the deepest thing. It's turns out to be a wonderful thing. But what I'm saying is like, okay, so if I drew the x-axis from A to B, and you have these like points along the axis, x1, x2, x3. But really, you're supposed to imagine them being like kind of, billions of points and so on. Well, this distance here is delta x, but what we're measuring in the Riemann sum, this expression turns out to basically be like this. So I'm saying this is like the change in G from, that's why I was saying like G1, right? And then it's like the change in G from this to this and so on. And you're going to get up to the last change in G. I'm giving them subscripts just to say they would be different numbers, right? They like delta x is always the same number, but if the curve's going up faster or slower, the delta G's, the change in the value of the function might be different. But you're just adding up all of these. That's what this sum is. The sum is saying add them up, bottom all up. And so the total, the sum of all of these, if we now, I'll even just go ahead and put like plus signs in between them, dot, 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 plus this equals the total change G of B minus G of A. Okay, and so that's kind of it. I mean, it's kind of, I'm not giving a really rigorous proof. You can give rigorous proofs, and if you keep going on, if you go take Math 2603 analysis, you'll find a more rigorous proof of this. But this is kind of the idea. The idea is that it's actually somewhat natural. But the trick is to imagine the function up here, imagine this function as the derivative of another function. And then you get to use the sort of this trick right here to like, you actually get some cancellation. You're actually adding up something somewhat natural. Okay. So that's my first argument. Second argument, which I claim is the same argument, is just pretend, let's look at the integral of, again, let's just rewrite the fundamental theorem of calculus. G of b minus g of a, where the derivative of g equals little f. Here's my second argument, and it actually harkens back to what we've been doing in the first, the past week, a week before. Pretend f of x is a velocity function. Tracking the velocity of some particle. Well, we know that the integral gives the change in position. From what we've seen, the integral is the change in position of the, in fact, maybe maybe what I really should do is make these into t's. It doesn't really matter what the variable is here. I can, right here, I could turn these all into t's. Maybe I should just be careful, do that. In fact, I just need those two to be t's. So if I want to think of it as time instead, that's not a t. What did I do? Okay, so there's a t. So, oh, and I guess I should change it here. I guess I should change them all here. One more. Okay. It's the kind of thing I do in class all the time, so might as well show you in the video. So is the change of position from t equals a to t equals b, right? But if f is velocity, but if v equals f of t, then velocity is the derivative of position. Then f of t is the derivative of the position function. And you might guess what I'm going to call it. I'm going to call it capital G of t. Right? And what's another way to state the change in position from t equals a to t equals b? So, but also, the change in position from t equals a to t equals b how could I write that in terms of G, capital G? Well, it's exactly just the position at time B minus the position at time A, right? That's how you find the change in position. If G of B is bigger than G of A, then it went forward, it went at the velocity, it's a net positive change. But if G of B is less than G of A, then it was a negative change of position, whichever way you decide, whichever direction you decide is positive and whichever direction you decide is negative. And so we have two different things that equal the same thing. They both equal the change in position. And therefore they equal each other. So yeah, the integral from a to b of f of t dt equals the change in position from t equals a to t equals b, which equals g of b minus g of a. So in fact, this gives another argument that actually connects to the stuff we've been doing, and that's kind of why we spent so much time looking at these velocity curves and estimating the position. But I really claim it's the same argument, because if you think about what we were doing in the Riemann sum, is we were looking at these little changes in position, these little distances. Each little narrow rectangle represented the distance traveled over a small time interval. So if you go back up to this picture right here, it's sort of the same thing, right? Like over each, now think of this as a time interval, over each time interval, we were measuring the change in position. And that was from basically the velocity times the distance times the change in time, right? So it's like a v times delta t, and that was giving us the change in position. And so in fact, it's the same argument, it's just in different clothing, but it's kind of remarkable. So I really think this is a nice way to think about it. And again, I'm just trying to get you to sort of respect the power of the fundamental theorem and think about why it's true, which is just, these are worthwhile endeavors in my mind. But next we'll move on to some more concrete things about properties of integration. So I will stop there.